Thank you for viewing this recorded Reliable Automatic Sprinkler Company webinar. Should you have any questions regarding this presentation, please feel free to contact Reliable Technical Services at 800-557-2726 or email us at techserve@reliablesprinkler.com. For upcoming webcasts and an archive of past webcasts, please visit reliablesprinkler.com/webcasts. Once again, thank you and enjoy the presentation.
Hello, everyone. Thanks for joining us. My name's Sam Schwander. I'm going to be joined by Mark and Pat here shortly with Perimeter Solutions. And today we're going to discuss foam water fire protection systems, or simply foam systems, and largely the industry's transition into the fluorine-free foams. So on the agenda today, we're going to give a brief overview of where we typically see foam systems, some of the standards used to design and install them, and we're going to go through the history or the evolution of foam products and then the regulations that kind of helped influence that evolution of foam. We're going to discuss the different types of foam systems, different components, valves, the different sprinkler systems used for foam. And then Pat's going to give us a NFPA 30 design example that will go into some great detail. And then we'll go over some performance testing, current solutions available to us today, and then finally hope to have some time to answer any questions that are out there. So let's look at some examples of where foam systems are typically applied, right? So we have flammable liquid storage. That tends to be our NFPA 30 design. Aviation, so that might utilize closed sprinklers, could be an open sprinkler deluge system, perhaps high expansion foam with foam generators. We have fuel loading areas, whole bunch of other industrial applications, kind of a wide net there. We've even seen foam systems required for parking garages. So that might be to supplement the standpipe system in the parking garage, or even we've seen it required for overhead sprinkler systems in these parking garages. Another common application, fuel oil storage. So something like a diesel fuel storage for a building's backup diesel generator is another common application. So NFPA has several standards they use for design and installation of foam water systems. So most of us are probably familiar with the likes of NFPA 13, NFPA 25, NFPA 30, which is flammable and combustible liquids, as I mentioned earlier. So we have some general standards that also incorporate foam. Then we have some more specific foam standards like NFPA 11 and NFPA 16. Now, should note that 2019 edition of NFPA 16 is the last edition of NFPA 16. So as of the 2021 edition of NFPA 11, that has absorbed all the requirements of NFPA 16. So you may or may not be working on those editions. You might be using NFPA 16 for some time, depending on where you are. And then we have some more specific applications, things like NFPA 409 or 418, aircraft hangars, helipads, a lot of different foam applications for those type of occupancies. So talking about foam system applications, how about the literal application of foam to a fuel? So when we apply foam to a fuel, it's going to do a few things, right? It's going to separate the fuel from the vapor, excluding the oxygen, smothers the fuel and prevents the release of vapors, and then the water content that's in the foam is actually going to cool that fuel surface. Some basic definitions of foam itself. So we have the foam concentrate that we're going to talk about. That's really that foam liquid in the concentrated state that is obtained and manufactured by a foam manufacturer like Perimeter Solutions. That's what we put in our bladder tanks. And then we're taking that foam concentrate and somehow introducing it and mixing it with water, our water supply. And then once we mix the foam concentrate with the water, we create our foam solution. So that's what typically will be distributed through our piping network of our sprinkler system. And then once that foam solution meets a discharge device, right, commonly a sprinkler, there's a whole bunch of other discharge devices, but foam solution discharges from the discharge device, gets aerated, and then it discharges as foam, and that's what's being applied to the protected area of our foam system. AFFF, that's aqueous film forming foam. And then now we have SFFF, which is synthetic fluorine-free foam. And important to note that fluorine-free foam does not contain any intentionally added PFAS. So talking about foam definitions, and I'm throwing an acronym PFAS at you. So at this point, I'm gonna hand it over to Mark Siem to talk about some other definitions, and he can speak on them a lot more intelligently than I can.
Thanks, Sam. I appreciate it. Yeah, so I'm going to go a little bit into this alphabet soup that's kind of been thrown around for the last few years, and so let's start out with PFAS. So per and polyfluoroalkyl substances. That's a group of chemicals out there, man-made chemicals that contains a carbon-fluorine bond, and those materials are found in fluorinated foams. So any foam that is fluorinated has PFAS, and that includes fluoroprotein, film-forming fluoroprotein, AFFF, and ARAFFF. And anytime you see the name fluoro or film-forming, just kind of associate that with having PFAS material in there. And then the new group of materials, or I guess the new synthetic group of materials, is the fluorine-free foams. So any foam that does not contain intentionally added PFAS. This goes all the way back into the the early 1900s with chemical foam, and then protein foam came along after that. This also includes medium and high expansion foams, syndet foams, so synthetic detergents. There's a place in UL for that, and then in 2021, NFPA coined the term synthetic fluorine-free foams to include the synthetic foams that don't have any PFAS in them. There we go. And so I went a little bit into the history, but this is kind of how the progression happened. So the chemical foam was a two-part foam. Mix it together, bubbles were made, CO2 is released, suppressed some fires, which is great. And then after that, they found that protein foam, using some of the components of animals, you were able to make a foam concentrate that, when diluted down, made a very nice foam that suppressed vapors, and you're able to extinguish liquid fuel fires. Then there were some synthetic high expansion and medium expansion foams, AFFFs, fluoroprotein foams, ARAFFFs, and AR protein foams. So like in the 1980s, it was found that there's a certain type of polymer that helped create a film or a mat, or coacervate, it's actually called, on top of a water-soluble fuel. And after that point, the industry was able to start creating foams to extinguish water-soluble fuels. Class A foams were developed in 1984. SFFs, those were originally developed in 2003, but most of that work hasn't happened, or hasn't really continued much, until probably about 2010, and then after that, the development really kicked in. Then in 2014, the first alcohol-resistant synthetic fluorine-free foam came out. Okay, so I'm going to go a little bit into the three main types that we may have dealt with in the past. So, chemical foam happened a long time ago. I don't think there are too many people around that have actually used it. But protein foam, like I mentioned, is made up of hoof and horn meal, blood and feathers. And it's that protein from the animal material that's hydrolyzed or chopped into small pieces, and that's used for making a firefighting foam concentrate. You chop up the pieces a little too far, you get really nice foam, but not very good performance. You don't chop up the pieces far enough, you get good fire performance, but you get a lot of sedimentation. So it's really trying to find a happy medium there for that hydrolyzation process. So not perfect, but it does work to put out a lot of fires. Until we had an incident at the USS Forrestal. So what happened here was a misfired rocket shot across the deck, ruptured a 400-gallon external fuel tank on an aircraft. That fire was not able to be controlled, and ultimately that fire consumed 21 aircraft, killing 134 people and injuring 161. So the military said, we can't have vessels out in the middle of the ocean that can start on fire or have an incident like this and not be able to extinguish those fires. So what came from that was the AFFF. So AFFF's made of a bunch of different components, hydrocarbon surfactants, solvents, inorganic salts. They all play well together in water, but the main component is the fluorosurfactant or fluoropolymer. And that's what gives the AFFF, I would say 85 to 90% of its performance is that fluorosurfactant there. So now we've got a product, an AFFF, that works really well. You're able to use all sorts of application techniques on putting fires out. Works great through sprinkler heads, no problems. So, but as that progression happened early on in the development of AFFF, there was one company, then another company came along, and then another. But over the course of about 60 years, all the AFFF, so if you had a 3% AFFF from company A versus company B, and they both had a UL listing or FM approval, they're going to be about the same in composition because the industry found a way to do it best, found a way to do it with the least amount of raw materials in there and at the best cost. So everything kind of gravitated toward that point. And then in 2010, the EPA came out with the PFAS stewardship program. So basically what this was to look at one fluorinated material and try to remove that from all the applications that use fluorinated materials, whether it's coatings on paper, firefighting foams, and a big one that's still used in is making the chips for cell phones. So what happened is they said, we want to get rid of this PFOA material, and that ended up turning into the regulated use of PFAS. So like I said, a little bit about the alphabet soup is trying to keep all these things separated and know what is what. But for PFAS, think of that as the umbrella, overarching genre of synthetic chemicals. And underneath that, there are thousands. It depends on what source you go to. Could be between 4,000 and 9,000 different synthetic fluorinated materials or PFAS materials. And the regulated use of that PFOA material turned into the regulated use of this whole genre of chemicals. And that ultimately affected the Class B firefighting side. So what we had to do is we had to come up with new products that did not have that PFAS material in it. And that was kind of a problem at first because we're trying to replace 85 to 90% of the performance of the AFFF. So I've got this guy up here not really sure what to do with his hands because he doesn't know what's in every fluorine-free formulation. It could be, each manufacturer is kind of doing it a little bit differently. And that's what you can kind of see on this graph right here is, company A, B, and C is not meant to represent any manufacturer of foam, just that different companies get in at different times. And right now, the technology between any manufacturer is going to be different. So we haven't reached that point of 60 years because we've only been doing this for about 20 years, developing these fluorine-free or no intentionally added PFAS-free foam formulations. So there's a lot of work left to be done to try to get all the performance of all the products up to matching that of AFFF. But there are a lot of applications, and I would say most of them for sprinkler heads where there is a viable substitute. So for foam in general, why is right now in the last maybe 4 or 5 years has foam been under the microscope for environmental issues? Well, in fact, foam always has been an issue because Mother Nature needs to deal with anything that's added to it, whether it's a spill or a discharge. So toxicity, biodegradability, BOD loading, so biological oxygen demand, loading, and then treatability at the local POTW. Those things have always been concerns. And then, over the last few years, the use of PFAS has really been looked at, and the industry is moving away from that sort of chemistry. With regulations now in the United States, here's a map. I use a website called Safer States, and they let you sort where the PFAS is used. And what you're looking at is a map of the states and where there's either an introduced law, an adopted law, or an introduced and adopted law to help regulate the use of PFAS in firefighting foams. if you were to look at the use of PFAS in all industry, most of this map right here would have some sort of color to it. But in terms of firefighting foams, this is kind of where it's at right now. Okay, so this is relatively new. So the EPA came out with a primary drinking water regulation. And the reason why I mentioned drinking water is because, this isn't processed water, this isn't wastewater, this is drinking water. And on April 10th of this year, they decided that there were some limits in there that they were going to set for, a goal and then also a maximum allowable level. And I bring this up because a lot of the local and state laws are going to be written around what the EPA comes out with. So just as a frame of reference, we're looking at 4 parts per trillion for PFOA, the main material that kind of started all this. And that's equivalent to 1 drop in 5 Olympic-sized swimming pools, or a grain of sand in 13 million dump trucks, or 1 second in 7,925 years. So we're looking for something very, very small out in the matrix of water. So that's why we say no intentionally added PFAS, because there could be some in the water coming into the location that the foam's made, or there could be a release agent that's used in one of the packaging materials that may have touched something at one point. So that's kind of where we're at, is we're looking at those levels. So we got to be careful, the whole process when it comes to making firefighting foams. Okay, so to ask, does my foam contain PFAS? So any of those carbon fluorine bond materials. So an AFFF, like I said, AFFF, fluoroprotein, film-forming fluoroprotein, yes, that material is going to have PFAS in it. You'd want to talk to the manufacturer on if it contains PFOA or PFOS, but as for the genre of chemicals, it's going to have PFAS. The other synthetics group, you're going to want to ask the manufacturer, but for the most part, those don't contain any PFAS, but just it's best to reach out to the manufacturer to ensure that it's coming from their mouth, not my mouth. Protein foam, this is just basic protein foam, not film-forming protein foam, not fluoroprotein foam, just regular protein foam. And then synthetic fluorine-free foams. PFAS should not be present, but it's always best to verify with the manufacturer that that is the case. All right, now I'm going to hand it over to Pat.
All right, so kind of moving into the fixed system side, right? So the good news is we're using similar types of systems to proportion the foam concentrate into the sprinkler system, and most of the time we're using bladder tank systems, right? There are other types of proportioning systems like foam pump systems that we don't have time to get into. But generally speaking, we use what's called a balanced pressure principle. We're balancing the pressure of the water in the system with the pressure of the foam concentrate going into the riser. So typically, we want to kind of think of this as a kit, right? In a perfect world, your bladder tank, the foam concentrate, and the proportioning device are all made by the same manufacturer, because when we take these products to UL and or FM, they're tested together and we find an acceptable flow range that these products work in. So how this kind of works here is, you can see in our model, we're taking a little bit of water pressure off of the system. And then inside of a ASME pressure vessel, we have a bladder that has the foam concentrate. So the water squeezes the bladder material, forcing the concentrate out into the green piping here. We'll have a hydraulic concentrate control valve. So off of the sprinkler valve, we need to have a sensing line that's going to open that up. So when the system turns on, that's going to open up the foam valve and allow the concentrate into the proportioner. So there's 2 different types of proportioners that we're going to talk about. The first one depicted here being a ratio controller. So now when you look at this system, one real good benefit of bladder tank systems is this is all mechanical. There's no outside power required to it. So if you have water pressure on the system, you have foam out in your riser piping, and you have fire protection. Okay. So moving on. to proportioners. Whoops. So there's two types of proportioners that we want to be aware of. All right. So ratio controllers and variable range proportioners. And you can kind of see on here, we have this chart of different concentrates with the ratio controllers. And that's really to kind of illustrate that every single foam concentrate that has a UL listing and FM approval has to be tested with a given orifice plate to get proper proportioning. So what we're doing with a 3% solution is we have a range that's acceptable, 3% on the dot up to 3.9% proportioning. And that's these ranges that you see here. So when we're talking about changeouts, something to be aware of is on this chart here, there are some older AFFF products and there are new fluorine-free products. So say, for example, you have a 3-inch ratio controller now, that UL listed flow range might be different with the AFFF foam versus the fluorine-free foam. So when we're talking about upgrading some of these older legacy systems, it's not just as simple as draining a tank down and putting the new products in. We need to make sure that the proportioning devices are also matching the flow rate of the system. So these devices we're generally using with fixed flow. So something like a deluge system, something where you have monitor protection around a diked area or a truck loading rack, something like a foam maker or foam chamber on flammable liquid storage. So even though we have a wider range of flows here, it's something that we're using where we know what the flow rate is for that system and it's not necessarily going to change. Now, if we're doing something where we might have closed head sprinklers or a wider range of flows, we're going to use what's called a variable range proportioner. So this device is designed to operate down to a flow range that would cover 4 of the most remote heads in a system up to the design area. So you can kind of see here for one of our fluorine-free products, we have a flow range of about 35 GPM up to approximately 2,700 GPM, which is pretty great. And you might say, well, that's awesome. Why don't we just use this device for everything? And you can kind of see a cross section of the device here and how this really works. There's a wafer in the water path, and as the flow increases, it's going to push that more and more open. And the center tube there has a cut in it, and it's going to expose that, allowing more and more foam into the riser system. So as having something in the water path, as the flow rate increases, you're going to have higher levels of friction loss across the device like this than you would with just a ratio controller. So we're using this for something like flammable liquid storage in a warehouse, closed head sprinklers, or something where you might have one proportioner covering multiple zones with very different flow rates. So 2 different types of proportioners we want to be aware of. So typical installations of bladder tanks, they come in 2 different configurations, right? Horizontal and vertical. Now, being an all mechanical system and a balanced pressure system, right? We want to have the bladder tank relatively close to the point of injection. So once you get over a certain feet away, the pressure from the system can't take up the losses in the concentrate line. So these proportioning devices, they're modified Venturi type devices. So they're using the flow across the proportioner to have a lower pressure drop area. That's going to take up the friction loss in the concentrate piping. So that is one downside of bladder tanks. We want to keep them relatively close to the point of injection here. Another thing is that we don't want to have differences in elevations. You can see the horizontal tank here. The proportioner is a little bit above the tank. We don't want to extend that to different floors, right? We don't want to have a bladder tank in the basement and then the proportioner, say, on the first floor, something like that, because again, we want to reduce friction loss and head pressure in the concentrate piping. Okay. All right. So again, with vertical versus horizontal tanks, inside of these tanks, the bladder material is supported by the flange connections. So in a vertical tank, you can kind of see there on the left, it's got that top flange, and then underneath the skirt support, there's another flange that holds the bladder material in there. Once we start to get over about 900 gallons, 1,000 gallons, we start to kind of, look at maybe a horizontal tank as a better option, because you have 4 points of contact in there, that's holding and supporting that bladder material. So keep that in mind. Now, as far as materials compatibility, you can kind of see on the left here, the concentrate line is stainless steel. So we recommend brass, bronze, stainless steel for the concentrate piping. So keep that in mind as well, which is pretty consistent with what we've been recommending for AFFF systems as well. Also, we can supply multiple different systems with multiple different risers with one bladder tank. If we're doing that, say we have a system that has 3 different zones, maybe a truck loading rack, and then a second zone for the warehouse, we're designing that system so the bladder tank capacity can supply the largest demand on there. So you can have one bladder tank supplying multiple zones. And then here we have an example of a main tank and a reserve tank. So this is something that is more common in the aviation world. So this is actually right out of a foam system that was done a few years back at a Group 1 hangar. NFPA 409 used to call out a main and a reserve tank. That has since kind of gone away, but they opted to maintain the main and reserve tank in that case. So that's a manual transition. So if the system were ever to trip, somebody has to go in there and manually put the reserve tank in service. And then you can kind of see on the right here, we have 6 deluge zones supporting that Group 1 hangar. All right.
Awesome. Thanks, Pat.
Here. Yep. So back here to Sam for the system valves.
Awesome. Yeah. Thanks again, Pat. So now that we've kind of done a overview of foam and the foam systems, kind of want to get into a little bit more detail with the systems that we'll see and the types of valves that we use for these systems. So talking about fire sprinkler systems. So we can do foam systems with wet systems, dry pipe systems, deluge, and pre-action. So any type of fire sprinkler system that we're used to, we can support that with foam. And again, we're mostly going to be focusing on bladder tank systems in this presentation. But what I wanted to do is kind of use the model DDX valve as our example, because it's such a versatile valve that we can really touch on different systems with this one valve. So basically, the DDX valve is a mechanically latching clapper style deluge valve. So it's a UL listed and FM approved valve. Wide range of valve sizes available, 2-inch through 8-inch. Depending on the different trims, it can be listed for up to 300 PSI. And it's a deluge valve by design. The platform of the DDX is as a deluge valve, but we have different trims that we can make it a low pressure dry pipe valve, deluge, as I mentioned, or then all these different pre-action systems. So single interlock pre-action, double interlock pre-action, non-interlock pre-action. So with this one valve, we can kind of touch on 3 different types of systems: dry, deluge, and pre-action. So real quick, just to highlight the operation of how the DDX valve works. So the same water supply pressure that's going to be serving our system, we're going to tap off and pipe that to what we call a push rod chamber. So we're putting hydraulic pressure into this push rod chamber, which forces a push rod into the valve body, acts against the latch, which holds the clapper shut, hence the mechanically latching clapper style valve. So downstream, or at the outlet of the push rod chamber, we're going to pipe that to some kind of actuation device, and that's going to vary depending on the type of system we're doing, whether it's dry, deluge, or pre-action. But when we set the system, we're going to set the actuation device, and when that actuation device is closed, it allows that hydraulic pressure in the push rod chamber to build and set the system. So when the system is going to activate, we'll have our actuation device open, which allows all that hydraulic pressure in the push rod chamber to vent. Push rod retracts into the push rod chamber. Now our water supply pressure forces the clapper open, floods our system piping. And once that clapper opens, that same water pressure can get into what we call an intermediate chamber through those little holes in the seat of the valve and make its way to that alarm line that you see on the bottom right corner. So we're going to take that same water pressure, hydraulic pressure, into our alarm line and utilize that with our foam system. So we're just going to take another step back here, and we're going to look at the DDX valve incorporated with a bladder tank system. As you can see the cutaway there on the diagram on the right. So at the bottom left, that's just a nice, pretty isometric of a model DDX deluge valve. So in this example, we're looking at electric actuation of the deluge system, and we're going to have some kind of electric detection, releasing control panel. So now that actuation device downstream of the pushrod chamber is a normally closed solenoid valve. So once we get this system set up, I just want to note, we have that bladder tank, which is that pressure vessel, and that water supply pressure is going to be existing in that bladder tank before the system is stripped. So we're squeezing that bladder in that bladder tank and forcing that foam concentrate up until that normally closed hydraulic ball valve that you can see on the right there. So we're going to have foam concentrate up until that hydraulic ball valve. So if we have a detection event and our releasing control panel opens up our solenoid, now all the water pressure can dump to a drain, trip the DDX valve. The water can then get into the intermediate chamber of the valve to the alarm line and the alarm line trim. So at that top left, that blue highlight is showing us where that alarm line is normally being pressurized. So if we want to introduce this bladder tank system to a normal deluge system, we're going to remove that little 1/2-inch plug from what we call a multi-port fitting and pipe that to that hydraulic ball valve. So what's going to happen is that water is going to continue to that hydraulic ball valve, operate it open so that foam concentrate can continue its way to the proportioner, where it's then introduced into the water supply. We're then mixing that concentrate with the water through the proportioner at a set rate. And now we're bringing foam solution through our pipe network. So we're going to step back once more. So we have our deluge system, right? So open sprinkler or open nozzles. So that foam solution is going to travel through that pipe network, make its way to our discharge device. In this case, it's going to be an open fire sprinkler. So once the foam solution hits the discharge device, the fire sprinkler hits the deflector, it's being aerated and discharged as foam. So as we mentioned in the definitions at the very beginning, once that foam solution hits the discharge device, it aerates, becomes foam, and that's what is being applied to our protected area. So if we step back, looking at that Lehigh Valley International Airport example, it just helps to kind of look at those components in the real world. So obviously we have that DDX deluge valve, that alarm line at the bottom right hand of that photo where you can see that red water flow pressure switch. Off of that is where we're going to pipe our alarm line to the hydraulic ball valve, which you can see at the top left of the photo on the right. So then the photo of the bladder tank or bladder tanks on the left, we can see where our foam concentrate piping comes out from the flange. That's going to make its way to that hydraulic ball valve. So when this valve opens, that water supply pressure is going to make its way through that alarm line, open up the hydraulic ball valve, and then allow the foam concentrate to be introduced into that proportioner, which we can see at the top right of the photo on the right. So kind of to circle back to our different systems, that was just an example with the DDX deluge valve. And again, that can be used with the DDX LP low pressure dry, DDX pre-action, anything that the DDX valve can go into a pre-packed cabinet. So we can still utilize a pre-packed cabinet with our foam systems. But regardless of wet systems, dry systems, pre-action systems, the whole idea is as long as we have alarm line trim, we can pipe that to our bladder tank to introduce foam into our sprinkler systems. So, if we have an alarm check valve like the Model E, we can utilize the alarm line of the Model E check valve to pipe to our hydraulic ball valve. Same thing with the Model FX, which is a differential style dry valve instead of a low pressure dry valve like the DDX-LP. Same idea with the alarm line trim piping to that hydraulic ball valve, or even a diaphragm style deluge valve like the Model DDV. We have an alarm line that we can also pipe to that hydraulic ball valve. So we need discharge devices to turn our foam solution into foam. So A discharge device is exactly that, a device that's going to aerate and discharge that foam solution, creating foam, applying it to our protected hazard. So some examples pictured there on the right: hose reel, foam chambers. Today we're going to be focusing on fire sprinklers as the primary discharge device. So I threw a QR code on here just to direct you to that fire sprinkler web page where it shows all of the perimeter solutions foam concentrates and then all of the fire sprinklers UL listed or FM approved with those devices. So these foam concentrates, as Mark and Pat discussed, they're going to be UL listed, FM approved, or both with specific sprinkler models. So the sprinklers, they're going to have unique design characteristics based on things like orientation, whether it's upright or pendant, K factor, right? 5.6, 8.0, 11.2 K factor. So this list here is detailing all the perimeter solution foam concentrates that are UL listed or FM approved with fire sprinklers as discharge devices. And again, that's what that QR code is going to take you to. But let's say we have an application where we're requiring UL listings and we want to select the RF3 foam concentrate for a hydrocarbon fuel, right? So we could look at the fire sprinkler discharge device tables, select the foam concentrate, in this case, the Solberg Rehealing RF3. And if we're looking at the different designs, you can see based off of upright, pendant, K factor, we can select a sprinkler that's going to then tell us what our minimum application rate or density is, and then the minimum operating pressure at the sprinkler. So if we knew we wanted to use a 5.6 K factor quick response pendant, right, we could select the model F1 FR56 pendant, which is RA1414. And in that design, we will require a minimum density of 0.16 at and minimum 7 psi at the sprinkler. So now I'm going to hand it back over to Pat. Let him go into a example here.
Yeah, so let's put a little of that into practice, right? And again, keeping in mind that the foam side of this is kind of a kit, right? With the proportioning devices and the sprinkler heads. And another thing we want to point out is application density with the listing versus what maybe just the standard says. So for this example, we're looking at flammable liquid storage in a warehouse. We're going to assume that there are polar solvents stored in this warehouse, rack storage, at least 3 racks high. Okay, so for laying out the foam equipment, we're going to work with NFPA 30. We're going to say that the customer has a requirement of a UL 162 listing for the foam and the equipment, and we're designing to that NFPA 30 standard. Okay. Now, a few things out of the standard here that they're going to call out is a minimum of an 8K sprinkler head. Typically, we're working with a design area of 3,000 square feet out of the standard, a minimum application density with this 8K head of a 0.3 gallons per minute per square foot. And keep that in the back of your mind what the standard says versus what we'll talk about on listings. Minimum runtime of 15 minutes for the foam duration. That's how we're going to size the amount of concentrate that we need, right? And there's several different in-rack orientations and configurations that you can consider. For the sake of this example, we're going to say, out of the standard considerations for the 6 most remote heads per level of rack. So 3 levels of rack, 18 heads. Okay. So starting out with that, and we move here, the first thing we're going to take a look at is the discharge device. Now to what Sam was talking about, again, with the listings with the device, we're using an alcohol resistant type fluorine-free foam. That's always where we start with foam systems. What fuel that we're working with, that will dictate what foam concentrate that you're using. And then once we know what the foam concentrate is, we will look at what sprinkler heads are listed with it. So off of our chart here on approved heads, we find a 8K head rather, right? And we look at what the UL listed application density is for alcohols. In this case, it's a 0.37. So for that given head. Now, every individual head, and Mark will talk a little bit about this later, but every individual head is tested with the listing agencies and has an approved application density. So one 8K head might have a slightly different application density than another. But one thing that's consistent with fluorine-free foam versus the older AFFFs is that on polar solvents, we're seeing higher application densities with closed-head sprinklers. Just as a class, a suppressant agent, generally a little bit higher. So NFPA 30 is calling out a 0.3 gallons per minute per square foot, but the listing's a 0.37. So we're going to default to whatever's higher. So in this case, we're designing around a 0.37 gallons per minute per square foot application density with this 8K head. So looking at a side-by-side comparison, right? An AFFF may have been able to acquire a listing at a 0.3 on alcohols, whereas the new foams need a little bit more because without that film formation, we're relying much more heavily on the dense bubble structure. And you can kind of see if we have new construction, not so much of a problem, right? We're doing our hydraulic calcs and design around the new application density. If we are looking at a system that needs to be changed out, now to maintain that UL listing, we're going to have to increase our density from a 0.3 to a 0.37. There's a few implications that has on the system, right? So obviously a higher flow rate for the system. That's also going to increase the capacity needed for that 15-minute duration. So you're going to have a slightly larger tank. So when we're talking about system changeouts, it's not as simple. Again, there's not necessarily a drop-in replacement. So I think some folks get confused. They're like, look, we're just going to drain the tank out and we're going to fill it back up with the environmentally, more friendly concentrate. It doesn't necessarily work that way. We need to be aware of what the new application densities are and how that's going to impact the equipment of the system. Now, one thing to note on here with the hydraulic calcs, or not the sizing the foam tank, we have what's called a balancing factor in here. This isn't something that UL and NFPA make you do, but it's general good practice to have a 1.15 balancing factor. For FM projects and FM safety data sheets, it is a requirement for your calcs to have that balancing factor in when you're calculating the foam concentrate requirements. So this would be for the overhead. And for the in-rack, well, before we get to that, again, where we have closed head sprinkler system, so we're going to be using a variable range proportioner because, we need to have that operation from the foremost remote heads up to the design area, that 3,000 square foot. So we'll take a look at the proportioners that are listed with the foam concentrate, check out what the approved flow range is, and, we're using that 6-inch variable range proportioner here for that. For the in-rack. Because the way that NFPA 30 is written for the in-rack, they are calling out a flow per head, not necessarily an application density. And because the standard is calling out a flow rate per head, that 30 GPM, we're going to consider that as being the same, right? So 6 most remote heads per level of rack for this example, and we're going to get our flow rate based off of that and our runtime for the concentrate required for the in-rack. Now for the whole system, we're going to combine those two numbers together. To get our flow rate for the whole system. And we need to make sure that the overhead and the in-rack flow rates combined still fall within that UL listed range of the proportioner. And then based off of that 15-minute runtime at a 3% concentration, we're going to get the gallons of concentrate that we need. So here's what a bill of material of just the foam equipment would look like for the proportioning system, laid out here. So you have the vertical bladder tank, the 6-inch variable ratio controller, the hydraulic concentrate control valve. Now, typically, we will size the concentrate piping to the inlet size of the ratio controller. In this case, it's 2-inch piping. I think I saw somewhere in the chat someone was asking the feet of pipe to keep the bladder tank. A good general rule of thumb is approximately 35 feet of equivalent length. We depends on the type of concentrate. We do have friction loss charts for different given concentrates, but generally a good rule of thumb is approximately 35 feet of equivalent pipe on there. We can reduce that, of course, by increasing concentrate piping size, things like that. But for this example, this is the bill of materials for the foam concentrate proportioning system. And if you look on a side by side, right, the older alcohol resistant AFFF versus the new alcohol resistant fluorine-free foams, main keys here are the higher application densities that are listed with UL and FM are going to impact the flow rates of the systems and ultimately the amount of concentrate that you need to have for that system. So again, new construction, not a big problem. We're just designing around the new densities. With a change out, something you need to be aware of. Can the system handle that higher flow rate? What are the considerations on the room for the bladder tank to increase that size and the proportion are on there. All right, so I think I'm going to hand it over to Mark here to talk a little bit about the testing of the products.
Thanks, Pat. So just something to think about, as an installer, end user, or designer. The products that we make aren't designed to specifically work for your 10,000 square foot, 20,000 square foot facility, because we don't do fire testing on that size or that scale. So we have to rely on performance fire testing. And Pat and Sam have mentioned, a UL listing or an FM approval. Basically, that draws a line in the sand for minimum fire performance. And the industry has found over the years that a UL listing with a sprinkler product or an FM approval with a sprinkler product is sufficient for some of these applications. But I'm just going to go a little bit into the differences between those two fire test standards. And should be advancing. There we go. And just to kind of let you guys know that for the most part, the tests are very similar in terms of general flow. But the big difference is that UL does a test at 15 feet, about 15 feet above the field surface. And FM, you have to do a low height and a high height. So that's where you'll see some differences there. And then the other big difference is the UL sprinkler grid is a 12 and a quarter by 12 and a quarter spacing. The FM sprinkler grid for testing is a 10 foot by 10 foot spacing. So those are the two big differences between a UL listing and an FM approval, and how that plays into effect. So the total square footage on the 12 and a quarter and 12 and a quarter is 150 square feet, but the FM 10 by 10 is 100 square feet. So application densities for the fire test are a little bit higher for FM, but they also have that part where you have to find the low height at which it works and then the high height. And what we'll see is that the low heights usually ends up being around, say, 6 to 8 feet, and the high height, it depends on the height of the fire test laboratory that the testing's done. Now, for example, our test facility in Green Bay, our ceilings in our test building are 50 feet. So you'll see a lot of our sprinkler heads are listed up to 49.5 feet. And that's just because that's all the space we had. And that could be the case with any manufacturer out there, so they just run out of space to do it. So I'm going to go into two products here, and Pat and Sam have mentioned both of them. So the Rehealing RF3. This is a hydrocarbon fuel only. This is FM approved, UL listed. This was the original product out there that was fluorine-free foam that worked through a non-aspirated sprinkler. And this kind of set the bar for what could be done with fluorine-free foam technology. It works in fresh and salt water, and it contains no intentionally added PFAS. So this was a really big product for us and I think we launched it around 8 years ago. So there have been fluorine-free options for sprinkler applications for about that long. But the big technology jump came with the development of our Solberg Rehealing 3x3 SP100. SP stands for sprinkler. And, no intentionally added PFAS, but this is a hydrocarbon and an alcohol resistant product or polar solvent product. So it was the first one out there to have a UL listing on polar solvent fuels through a non-aspirated sprinkler head. So if you had, depending on, as Pat mentioned, you really need to know what your hazards are beforehand. And if you have water soluble fuels or polar solvents or the need for an alcohol resistant foam, this would be the route you'd go. And if you only had hydrocarbon fuels, you'd want to go the Solberg Rehealing RF3 route because that's going to be a little more economically friendly. And then if you're interested in looking at the listings and approvals for both those products, you can go to the UL Product IQ or the FM Approval Guide to get into the details of which sprinkler heads are listed. And then with FM, what heights, both high and low, and then the application densities that go with.
So just as kind of like a summary on change outs and things, I know there's a lot of questions and in many different states, there's different requirements on either timelines and changing things out. So again, in a perfect world, keeping in mind that a foam system is a kit, right? We, as best as we can, we want to maintain the listing, being consistent with the manufacturer and using a sprinkler head that's listed with the foam, right? Now, looking at the systems, one benefit, with the hydrocarbons, the original RF3, we have consistent application densities. So it's not all bad. It really depends on the fuel. For hydrocarbon hazards, like an aircraft hangar where jet fuel might be your main hazard, the application densities that we have with UL are consistent with what we had with AFFF. So a change out in a system that's protecting a hydrocarbon only type hazard might be much more simple than the design example we looked at earlier with NFPA 30, with a warehouse containing polar solvents, right? That's generally where we see the application densities increase. So again, really hitting on what are we protecting? That's always where we start. And then we can decide on what concentrate we're using. But yes, if we want to take a look at the sprinkler head, is that listed with the new concentrate? As far as a contamination level, Mark was saying about the low levels of PFAS chemicals that they're looking for. We definitely want to change out anything that is touched raw concentrate. We get questions about, can we try and flush a bladder tank? Can we try and rinse out the concentrate piping? And I would really recommend you don't try to do that for a number of reasons. One, the bladder tanks are not designed to be cycled like that. And there is a possibility that with filling it up and draining it and filling it up and draining it with water, that you can damage the internal bladder. You don't necessarily want to cycle these things over and over and over and over again. The other reason being, at those low levels, those parts per trillion that we're looking for PFAS chemicals, flushing the system like that is not going to get rid of all of that old material. And once you fill it back up with a new fluorine-free product, there is a potential to contaminate the new product, right? So anything that touches raw concentrate, we definitely want to replace, right? So at a minimum, internal bladder material, these bladder tanks, concentrate piping, and ratio controllers at a minimum, right? Now, again, we want to work with the authority having jurisdiction on what listings requirements there are, what design standards. In some cases, you might have a system that's 40 years old that was originally designed to an NFPA standard, and now that facility is FM insured, and now you have to design to an FM safety data sheet, right? So what are we designing to? That's also important. Application densities we've really hit on today, but just again, the application densities might change, and the proportioner size. Just because you have a 4-inch proportioner now does not mean if we change this system out, it might change. We size the proportioners on the tested flow range because we need to have that 3 to 3.9% proportioning, right? So it's not necessarily about pipe size, it's about the UL and FM approved flow range of those devices that are going in there. So quick rundown summary, right? Anything that touches raw concentrate, we need to remove and replace that. We're looking at this as a kit, trying to maintain listings as best we can here. The bladder tank, the concentrate, the proportioners, the discharge devices. And what design standards are we looking at with the new application densities? Hydrocarbons, we have consistent application densities with AFFF. So, pretty easy there. No hydraulic review. If you're working with polar solvents, be aware the new listings might be higher application density. So you need to check the UL approvals guide, or the FM approvals guide, and the UL product IQ, see what the new density is, and do you need to do a hydraulic review of that system. So those are kind of the key things that we're looking at on a system change out.
All right. Well, great job, gentlemen. As you might have guessed, there are a number of questions in the chat to go through, and it's noon now, so we're not going to go through them all, but I did have a couple that I wanted to run by you guys. First of all, one of the questions was UL and FM listing and approval test only simulate pool fires. What about containerized fires that generate two or three-dimensional fires, or jet torch fires, or ruptures or bleeds? Does listing approval represent actual industry situations?
Yeah, I'll take that. Sure. Yeah, it does, because two-dimensional fire is exactly what we're testing. When it comes to three-dimensional fires, jet torch fires, and levies, that's not foam is not a recommended use for those applications. That's where you'd want it. Well, not a sole use for it. You're going to want to use foam and a dry chemical for any three-dimensional fires that are there.
Okay. Second question. Can you provide a small piggyback tank for the additional foam required?
So, yes, you can potentially do that. So you just need to be careful for a couple of reasons. One, a new piggyback tank is going to have a different capacity. If we're going to have two bladder tank systems in parallel, we want to balance everything as best we can, right? Because you want the same pressure going to those tanks. You don't want one to drain down before the other. You can affect the balancing of that system, and it might affect proportioning. So it is something that is possible, but not really our go-to option. If you can increase a 500-gallon tank to a 600-gallon tank, I'd much rather you do that than add a 100-gallon bladder tank next to an old one, because balancing the system is going to be a little bit tricky.
Gotcha. Okay, let's do one more, and then the remainder in the chat, what we'll kind of do is after the fact, we'll go through and maybe I'll talk with Mark and Pat and Sam about what those questions are, and we'll try and respond to them individually. But one more for the group. First of all, are there any environmental concerns with the fluorine-free foams, and what are your disposal recommendations for swapping out AFFF?
Sure, I'll take those, Pat. Environmental concerns. There's environmental concerns with anything. For example, if a milk truck's going down the highway, it tips over, spills in the ditch, you're going to have a lot of grass kill there. Like I said, Mother Nature needs to deal with it. It doesn't really matter what it is. So what we're seeing is there's a little bit higher BOD, so biological oxygen demand with fluorine-free foams because there's more stuff in there. Because remember, we had to find a way to overcome that loss of about 85 to 90% of the performance by removing the fluorinated material. And then on the side of clear disposal recommendations, I can give you a list of some names of some companies that do the work, but as for regulations, you're going to want to work with your local EPA and the local government and the state government to figure out what's best for your area. Because you saw the map that I showed earlier on, and every state is doing things a little bit differently when it comes to these laws for what's acceptable and what can still be used.
That makes good sense. All right. So I'm going to guess this is a marker pack question. A lot of emphasis is being put on the sprinkler being listed with the fluorine-free foams. But to obtain the listing, all the foam and fire system equipment has to be listed with specific foam, i.e. the entire fire sprinkler system and foam system has to be demoed and reinstalled new if switching to fluorine-free. Is that correct?
I think that both Mark and I probably chime in on this one. No, I don't think you need to demo the whole thing. There are, again, anything that touches raw concentrate from a contamination level, we want to definitely do that. You could potentially replace a bladder in an old bladder tank, and put a new proportioner in and maintain the listing, again, keeping consistencies with the manufacturer. You may have to upgrade the sprinkler depending, right? And in some cases, we've worked with folks in the past to run sprinkler testing. So, and Mark could probably speak a little bit more on that. But no, it's not necessarily that you're demoing the whole thing. Mainly, we're looking at the proportioning system and the discharge devices.
Yeah, and it really depends. Yeah, and it really depends on the environmental side on what level of clean is clean and what's acceptable. Because if they come in and say, "Yep, we want to match the drinking water," well, then more than likely you're going to be at less than 4 parts per trillion, and anything that's touched PFAS is going to be considered contaminated.
Gotcha. So a very similar question here, kind of, I think, but just to clarify. So far as pre-primed AFFF systems, are you recommending that the existing pipe be replaced along with the components contaminated with AFFF concentrate?
Again, that's another, just what Mark said, right? Authority having jurisdiction, state laws, what their EH&S people are going to make you do. There are some companies out there that have different types of rinse procedures and things like that Mark, you probably know a little bit more about. But it's really a case-by-case thing, right? There's no one answer to that question. It really depends on the location.
Gotcha. All right, one last one. Are there any listings for use grate nozzles or oscillating nozzles?
Yeah, there are some, but more are coming. As different manufacturers come out with different hardware devices, we're looking at what's useful for us in our portfolio with our fluorine-free products, and we've flagged both those devices as important for the industry. So we expect to have those addressed by the end of the year.
All right, great. All right, any closing words before we shut this thing down, or?
No, just appreciate everyone joining us today, and reach out to Tech Services if you have any questions on our end. I'll be on the phones this week, so I'll be picking up the phone after I play catch up a bit here.
All right, thanks everybody.